All right, let's start the webinar. Let's start the class. So I hope you can hear me all right. Please write something in the chat.
We can hear you well.
Okay, great. So today we have a more theoretical webinar rather than usual. In fact, it's actually can be considered as a lecture inside the webinar. So we'll cover a new topic. In particular, we'll discuss the concept of exploration in reinforcement learning in some more detail than previously. So if we have some time after the theoretical material, then we'll move to the notebook. We'll discuss how exploration strategies can be implemented in GYM. And we'll discuss the homework assignment, which I will put right after the webinar. So let me share the screen with the slides. Okay. So as I have already briefly said, this week we have a brand new topic, which we have not discussed in any detail so far, only on a very shallow level. And this topic is about exploration in reinforcement learning. So once again, I hope by this phase of the course, you already know what do we need exploration for, why this problem occurs during training of reinforcement learning models, and what are the basic tools to incorporate exploration into training. But just to give a brief review, let's discuss it once again. So exploration and exploitation in reinforcement learning. This is a very common dilemma. So why do we need to explore during training and not always to pick optimal action? So the problem here is that during training, at each state and stage of the training, we have the current perception of the world. We train the agent, which knows already some concepts of the world. It has an idea not so good, and this agent makes the decisions to further train and improve its knowledge. But at the same time, we want this agent to have a decent quality. So we cannot always pick some random action. We need to do something sensible. So hence, this problem arises during training. So our information is always imperfect, and given this imperfect set of information, we need to decide how to act in each situation where our agent is at this point. So exploration, hence, is to gather more information and do something that the agent is not sure about. Whereas exploitation, as it goes from the name, is basically to act greedily with respect to the current state of knowledge. So our agent thinks that something is better than the other action, and when we exploit, we basically make the best decision given the current information. And as you probably understand intuitively, it's not very good to always exploit or to always explore to reduce uncertainty to the greatest extent. We need a combination of both. So we should, first of all, try to achieve the better performance at the end of the training. And secondly, in some applications, we need to have good enough quality during training. For example, when you are training some self-driving vehicles or something else, where errors can be critical. So yeah, agent should gather enough information to make reasonable decisions. And there is a saying, the best long-term strategy may involve short-term sacrifices. So that's the problem. And today we'll be solving this problem. And hopefully by the end of the class, you will have a more foundational knowledge of how can this problem be measured, what are the main techniques, and what are the main tools to decide kind of whether or not to incorporate exploration at some phase of your algorithm and to which extent. So actually, this is a not very difficult problem to comprehend, because in real life, us humans also can be seen facing this dilemma. So for example, when you're selecting a restaurant to have dinner, you can either go to your favorite restaurant, which you visit very often, and you kind of know what to expect, and you know that you should expect something pretty good, but nothing quite out of the ordinary. So you know that it is a safe choice, and if you go to your favorite restaurant, you will likely be satisfied with it. But on the other hand, you can try to visit a restaurant you've never been, and when you visit this restaurant, you can kind of be blown away by the quality, and it can be a better choice at the end. A more realistic example of exploration connected to reinforcement learning can be if reinforcement learning is being applied to some kind of advertisements. So for example, you're building a tool on the website to select which ads to display to the user. And for example, your ads display some video games. So the user visits the site, and you display the video game to recommend the user to play. So you can either pick the safe choice, for example, the most popular games, or well, this choice would be pretty standard, but at the same time a pretty good baseline, because the most popular games would be typically not very bad, and it is unlikely that if the game is very popular, a brand new user or the user which likes similar games would be dissatisfied with this game. But this approach has a problem that if you always select the most, if you kind of always select the game you are the most sure about, whether it's the most popular game or the similar to the user preferences, you would not explore all the variations possible, all the set of games that you can recommend to the user. And if, for instance, a new game is now available at the storage, for example, completely new game. So you know nothing about it, but it can be genius game. It can be quite a successful application, but using this strategy of going to the most probable recommendation given your current knowledge of affairs, this game would not be recommended to anyone. And even though it is a genius game, nobody will learn about it. So you need to somehow incorporate these cold start items into your strategy to somehow learn about them and let them and give them the opportunity to be recommended to someone. So now moving to details. So the first concept that is connected with exploration, and actually historically the problem of exploration was the most thoroughly studied in this example, is called multi-armed bandit. So what is a bandit? A bandit in real life is these games which can be seen in casinos or some other some other clubs. So those are slot machines where you put in the money and you roll the dice and kind of wait for the good outcomes to occur. Some time ago, long time ago, they were relatively common in Russia. So now in Russia, those are not seen very often, but in other countries, such as USA, those slot machines can be seen in casinos almost everywhere. So those are called multi-armed bandits. And they contain arms, because the arms are actually the actions that you as a user can take in these bandits. So you can pull, depending on the structure of the slot machine, you can pull either one arm or another. So there is a complete set of different arms which you can pull. And depending on chance and the arm that you have selected, you can get the prize or not. So the problem of multi-armed bandit is basically the problem of a user, of the agent in this environment. So when you come to the casino, you want to get as much prize, as much cash as possible. And you do this by choosing arms in these slot machines, and you need to kind of select the most promising slot machine, which will give you the most reward. So this is a fairly not very realistic example, because in the problem of multi-armed bandit, it says that you have several bandits, several slot machines, and each of them have different probabilities of success. So some slot machines are screwed and always output non-winning tickets, whereas others are more promising and you can actually win something from them. So when, as a user, you come to the slot machine casino, you need to pick the best machine and the best bandit, the best arm, in other words. So this is the problem set up. You have only one state, and in this single state, you select which slot machine to play. So you have n possible actions, n is the number of the machines. And each machine has an unknown probability of success. So some of them are better, some of them are worse, and you don't know that beforehand. And as the user of the casino, you want to maximize the total return. So you want to maximize the total cash that you win minus the cash that you spent. So the end goal is to maximize the money that you get. So in our formalism, to maximize the total reward. So how to measure? So basically, that's the problem set up. And what will be our metric? So we need to somehow explore all the slot machines. We need to try the first one, the second one, and so on. We need to try all of them. But at the same time, once we realize that one is better than the rest, we need to stick with it so that we don't lose. So that we lose as little money as possible. Yeah. So how to measure the success of solving this task? And basically, the metric for this is called the regret. So what is the regret? The regret is basically the difference between how much we could have achieved in ideal strategy minus how much we have achieved in our strategy. So moving to the notation, we have the Q function, which you all know about. It's the expected reward given the action. In this case, the Q function will be the probability of success in this slot machine. And you have the optimal Q function, which is introduced as the V star. So V star is the optimal Q function. Basically, it's how much you will get, knowing the perfect action and always selecting the perfect slot machine. So the regret is basically how much you would achieve in this idealistic scenario where you pick the best slot machine, and how you act, and basically what you have selected in your own experience. So we want to minimize the total regret, and trivially speaking, the best exploration algorithms would probably have the best regret, as you would explore the environment very quickly, and at the end you would converge to the optimal action, to the optimal slot machine. So are there any questions on the problem setup, or is everything clear so far?
So far clear.
Yeah, great. So now let's try to compare the algorithms that we already know, and hopefully we would understand what a good algorithm does in this case. So which exploration strategies do we already experience in this course? So the first one is Epsilon greedy. So you have seen it in the homework, you have seen it in the lectures, and it's the simplest exploration strategy of across all the others. So Epsilon greedy, nothing new here. So select random action with probability of epsilon, where epsilon is not very high. And with the rest of probability, select the optimal action in the agent perspective. So there is also decaying epsilon greedy, which is a slight modification where we change the exploration extent, where we change the epsilon as we progress during training and as we learn more about the world. So we start with high epsilon, for example, 50%, half of the time select random stuff, because we don't know a lot. And for example, every 1,000 steps, we decrease exploration rate to 1%. So after 5,000 iterations, we would stop exploring, for example. So there are other schedules, but this is just an example of linear decay to 0. So decaying epsilon greedy, intuitively speaking, is much more optimal, because we would stop exploring probably at the time that we would learn enough to rely on our knowledge. And the third one that we have discussed is Boltzmann sampling or softmax sampling. And it is basically a slightly more complex exploration strategy, where we pick not always the argmax, but we pick the softmax. So instead of picking the action with the highest Q value, we apply softmax transformation and pick the action with the highest probability given by the softmax. So this will resolve some problems where a lot of actions have similar Q values. We would not pick only the highest, we would select them relatively with relatively equal probabilities. So we can also introduce temperature here, given by STD in this formula. And this temperature can regulate the extent between the greedy sampling and the uniform selection. So those are the strategies that we have seen. So now let's try to compute the regret and compare them in case of multi-armed bandits. So firstly, let's look at the algorithm with no exploration at all. So greedy algorithm, which always selects actions with the highest current values. What will be the total regret? So the problem here is that greedy can lock to some suboptimal action forever. So for example, if you have five slot machines, and at some point of the game, you realize that the third one gives you $1 every 2 runs. So the average reward would be $0.50. And by this stage, for example, let's say all the other slot machines have not given you any money. So the utility of the third machine would be, so the Q value of the third machine would be half a point, because the average money that you get is one half of $1 per one run. And for all the rest of the machines, for the first, the second, the fourth, and the fifth, the utility, the Q function would be 0, because basically this is the estimate of the Q value for the slot machine. So you would so by the greedy algorithm, you would stick to the third one, because well, your estimate of the reward for this third machine would be greater than for all of the rest. So you would continue picking the third machine, and basically, because you would not get Q value less than 0 for this third machine, you would not switch to any of the rest. So basically, in this example of the bandits of slot machines, you would log to the machine where you receive your first money. But this can be suboptimal. For example, if the second machine is better, but due to bad luck, you have not seen any money from, for example, one first run in this machine. So even, for example, if the true probability of success in the second machine would be, for example, 80%, you would still get a decent chance that you would log to suboptimal machine, and you would not learn that the second machine is better. And what's the total regret here? So the regret would be linear. And why is it linear? So linear means that at each step, at each game, you get less than optimal. And total regret grows linearly with respect to the number of steps. So you get constant regret at each step, which is measured by the difference between the optimal machine and the suboptimal machine. So now let's move to Epsilon greedy algorithm. So Epsilon greedy with the constant epsilon is somewhat similar in terms of performance. It explores forever. And for example, let's say we have 20% probability that we select random action. And the total regret here would also be linear, because with constant probability of 20%, we would not select the best action. Even though we can know the best action, we would not select it. We would select random stuff with 20% probability. And hence, the regret here would also grow linearly with respect to the step, because at each step, you would add to the regret, to the loss, the constant difference between the expectation of reward for the best action and basically the expectation of the reward for the best action multiplied by the exploitation probability, which is less than 1 strictly in this case. I believe there were some pictures here, but for some reason they are not presenting. But I hope this is not a big problem. So epsilon greedy is also linear with respect to the number of steps, because we always get less than the ideal performance, and we would never converge to selecting the best action with regard to the expected reward. So what if we now have epsilon greedy with decay? So we would not have the problem where we always select some suboptimal action with the fixed probability. So here the main problem was that we had like 20% probability of random action or any other number. But here, if we pick the schedule correct, we would not have this problem, and ideally we would converge to always selecting the best arm of the bandit. And with a proper schedule, this leads to some improvement in performance. So initially we have some loss because we have exploration, which incorporates random sampling of actions, which are not ideal. But if we get the schedule correct and we reduce the exploration rate to 0 only after we converge to the correct ordering of actions, then after that we would always select the action with the greatest expected reward, and we would not increase the total regret anymore. So theoretically speaking, with proper selection of the schedule, epsilon greedy with decay has a logarithmic total regret. This means that the limits, so this means that in the limits, the total regret with regard to the step going to the infinity behaves more like a logarithmic function multiplied by some constant, which is much better than the linear regret that we had before. But in practice, it's kind of not very trivial how to design a schedule for your concrete environment, for your precise problem, because different algorithms have different rates of convergence, and if you explore too aggressively, you would probably make too many unnecessary steps with the random sampling. And if you explore too, if you decrease the exploration rate to 0 too fast, you would not converge to the optimal action. So in practice, this way of sampling becomes much more tricky when you try to apply different algorithms to different environments. So those are the algorithms that we have already seen in the course. Let's try to understand how we can design better exploration schemes which have good properties in terms of regret, in terms of making minimal regret, of getting minimal regret. But at the same time, we want to have this restriction that it should be relatively easy to understand which parameters of exploration do we need to apply for this environment. So ideally, we would need minimal tuning, but a good strategy that we can apply without modifications in different environments. So the first of the strategy is called optimism in the face of uncertainty, informally speaking. Probably it can be most easily explained if we look at some real-world analogies and try to understand how the humans explore. So, for example, let's imagine which of the following questions would we like to investigate. So the first one is whether the humans can fly by pulling the hair up. And the second one is whether the new cafe next to the office serves the good breakfast. So probably it's obvious to you that the action that we would investigate if we are sane is the second one, the question that we want to investigate. But so why do we make such a decision? So how can we formalize this decision-making process? So one logical idea is generally we want to try actions if we believe there is a chance that the actions are good. So the first one, we are fairly certain that humans cannot fly by pulling their hair up to the air, and hence it seems pointless to investigate this action, even though if it's correct, if somehow it is possible, then the reward would probably be very high. And the second one seems more realistic, and typically we expect that it is possible, and there is a decent chance that exploring this concept, this question, would lead to some good outcomes for us. So we want to try actions if we believe there is a chance they are good. So how do we measure this chance of goodness? How do we measure how much we believe in these actions? So let's try to look at this plot. And this plot represents three actions. So we have action 1, which is blue, action 2, which is the red line, and action 3 is the green line. So for each action, we have in our own minds, or in the memory of our reinforcement learning agent, we have a distribution of Q values. So each distribution tells the current approximation to the probability distribution of each action. So Q function here can be also thought as the reward. And these plots represent, for example, that on the horizontal scale, we have values of the reward. And on the vertical scale, we have the probabilities that this action will give us this much reward. So for example, in action 3, the argmax probability is somewhere between 2.4 or 2.8. So looking at these current estimates of probability, what do you think is the action that we should pick here? Just informally speaking, how can we, if we compare these three actions and our estimates of the rewards, which action do you think is the most promising here?
Green one.
Green one. Okay, so you think that it's the biggest integral. Okay, so different opinions. Okay, so why do you think the green one?
Smallest variance, highest probability of reward.
Okay, and why do you think the red one? Oh, okay, so you wrote in the chat with the biggest integral. So there are two, yeah, so it is possible to have different strategies of picking actions. You have mentioned two of them, and actually both of them are pretty logical. So the first one is to select the action with the highest expectation. So the expectation here would be just the extremum point of the probability, well, basically of the cumulative density function. Or I believe it's the probability density function here. Yeah, so the first strategy is to select the action with the highest expectation. And the second variant is to somehow look at the surface of the density function. But actually, I believe that you meant something different than the biggest integral, because the integrals here are all equal to 1 because of the property of probability density function. This is the distribution of the reward function due to built on the previous experiences. So we have some history of past events, and we have estimated the distribution of rewards that we get for each of the three actions. So we have samples of rewards for each action, and for each sample, we build the distribution over the sample. So we kind of want to have to estimate the probability of rewards by collected samples of these actions. So there are different strategies here. And they differ in terms of the rate of exploration and basically the properties. So that once again, I believe the previous explanation could be a little confusing. So once again, we can, on the one hand, select the action with the highest expectation with the highest average Q value. Or on the other hand, we can look, for example, at the percentile. So we can look at the 95 percentile of each distribution and see that the percentile of the green action is not very high, but the blue action, even though we know not a lot about it and the expectation is not very well, and the expectation is lower than the green one, there is a chance that the blue action actually is greater than the green one. So there can be different strategies for incorporating and using randomness of the past experiences and estimating the properties of the distributions of rewards. So, for example, one of the concepts relies on the uncertainty. So uncertainty is some more or less vague concept, but in probability theory, we can formalize it. And for example, we can estimate the entropy of the distribution. So the highest entropy basically means that the uncertainty in this distribution is the highest across the different distributions. So for example, here, the uncertainty and the entropy of the distribution is the highest in case of the blue plot. So the blue plot is the most, how should I say it? Well, basically, it's the most distributed across the axis of rewards, and that means that we are not sure what we would get in case of selecting this action, and we could explore in this way. We could compare the uncertainties or the entropies of the empirical distributions of Q functions, and we could select the action with the highest uncertainty, with the highest entropy of empirical distribution. So in this example, this would be the blue action. So we know not very much about this action, and let's say we want to explore very aggressively to understand with the good precision whether or not this action is better than the others. So it could actually turn out that our current estimate is skewed to the left, and the true expectation value could be around here. So who knows? Let's try and decrease the uncertainty by selecting the most uncertain actions. So let's say we have selected the blue actions because we were not very certain about it, but when we have the new experience, we have new data points, our probability density function becomes much more centered. So the domain shrinks of this function. So now we have more data points and we understand more properly that the main domain of the rewards that we would get by this blue action is much less than of the other ones. So after picking this action, we are less uncertain about the value and more likely to pick another action. So this is the first strategy of exploring. So if we want to explore the environment very aggressively, we could always start with the most uncertain actions, with the most uncertain in terms of our current estimates of probability distributions. Yeah, so this is a viable approach because using this technique, we would explore the environment and most likely we would not leave any areas of possible strategies uncovered. So we always explore the most underexplored actions, and after time, this would lead to the fact that we have explored all the possible actions, all the possible strategies, and kind of we know a lot about the environment and can understand which action we should take. But this is not very logical because sometimes, even though some action is more certain than the other, we would probably pick the action that we are most certain, because even though other actions have greater entropy, we could understand that they are still the worst. So the best action can be the one that we are most certain about. And the strategy would continue to pick actions with the highest entropy, even though we may be sure that they are worse than the rest. So in the strategy, for example, we would continue picking the blue one because the blue distribution has still the greater entropy, but we understand clearly that the green action is the better. So a more sophisticated strategy is called upper confidence bounds. So it builds upon the idea that we want to select uncertain outcomes, but here we look not only at the uncertainty, not only at the entropy, we also compare the expectation. So we want to select ideally both uncertain outcomes to explore, but we also want to select the greater expected value. Because in our previous example, well, it's clear that the expectation for the green action is greater than the expectation for the blue action. And even though the entropy here is greater than in case of the green one, it's pointless. It looks pointless to explore this action any further because there is a very low probability that the true expectation for the blue action would be greater than the green one. So another way to do this is by using upper confidence bounds. So if you have seen this in the statistics course, you're probably familiar with this idea. So upper confidence bound is basically the value that, according to our estimates, exceeds the value of some distribution with a given percent of chance. So if we are given some probability distribution, which we draw samples from, we can use different confidence bounds, and the confidence bound would be a number which exceeds the sample drawn from this distribution with the given probability. So upper confidence bound is basically the bound which bounds the sample from the distribution from the upper side. So this strategy, upper confidence bound, basically works with the optimistic estimates of the distribution properties. So, with formally speaking, looking at this plot, the naive upper confidence bound would be to use something connected to the sample percentile. So, for instance, we could draw 95% percentiles from these three samples, from the green one, from the red one, and from the blue one, and compare them with each other. So probably the 95th percentile would be the greatest for the red distribution, and in the strategy, we would select the red one, the red action. So why is that? Well, intuitively speaking, the measure of the optimism in different actions is this percentile statistics. So 95% percentiles kind of measures how good this action can possibly be without being too unrealistic. So in case of these three in case of these three probability density functions, the greatest percentile would be with the red probability function. And intuitively speaking, well, this encapsulates the idea that we want to try to look further at the samples drawn from the red action because they may be better than the green one, well, by using both sample mean and the sample variance. Can we incorporate skew and select density function which is most skewed to the right? Question from the chat. I think if we select skew without looking at the expectation, if we select only only distribution which skewed to the right, we would probably end up in the situation where if there is a distribution which is not centered, for example, located at this region, we would end up selecting this one. So if we just look at the skew, we would probably lose information about the average. So we need to combine them together somehow. And a good way to do this is by using percentiles or something else. So a percentile is not very theoretically sound measure of uncertainty. The better way to do this is by using Hoeffding's inequality. So Hoeffding's inequality is the fact from probability that can measure upper confidence bounds with good precision. So this inequality says that given a sample of random variable bounded in the interval between 0 and 1, we can bound the probability that the true expectation exceeds sample mean plus some deviation by the exponent of the product of the squared deviation times the number of trials. So T is the number of trials or the sample size. So if the sample size becomes large enough, then given fixed U, given fixed deviation, the probability that true expectation is very different from sample mean converges to 0 in the limit. So we can apply this inequality and get upper confidence bounds. So we want to have some upper confidence bound based on our samples. This would be UT of A, upper confidence bound by U. And we can kind of estimate it to be dependent only on the probability in the Hoeffding's inequality and the number of trials. So given the fixed probability of deviation. So in the case of 95% confidence bound, it would be 2.5%, because the deviation works in two directions. And given the sample size, we can estimate the upper confidence bound by the square root. So in this case, in the case of 95% upper confidence bound, we can estimate the upper confidence bounds to compare as minus log probability divided by 2 multiplied by the sample size under the square root. So not to be confusing in the math, the core idea of this Hoeffding's inequality and upper confidence bound is that we want to bound the expectation of the distribution using sample mean and some other statistics. So these statistics that will be used to bound true sample mean, true random variable mean, true expectation, is given here as UT. And the probability that the sample drawn from this distribution is greater than the sample version of Q function plus these statistics can be bound by this exponent. So to deduce here the statistics for upper confidence bound, we kind of use the probability of upper confidence bound as given, and we use the number of trials, which is the sample size here. So for example, we want the upper confidence bound for 95% probability, and thus we can estimate this upper confidence bound, this statistic that we add to the sample mean as the square root. Yeah, so I believe this is relatively common in statistics to estimate the upper confidence bounds this way. So knowing this concept, knowing how to estimate upper confidence bounds, we can compute upper confidence bounds for each action and compare them with each other. So the most optimistically promising action would be the one which has the greatest upper confidence bound of true expectation, of true Q-value here. And we can estimate these upper confidence bounds, once again to summarize, using sampled average Q and this UT statistics that is computed from the probability, for example, of 95% and the sample size. As the sample size becomes higher, the interval, the confidence interval for the expectation shrinks. And basically, we are more certain about the fact that true Q-value becomes close to the sampled version of average Q-value. So I hope that now the explanation is more or less clear. So there is a possible extension of this upper confidence bound sampling strategy is to reduce P during training. So why do we need here? Why do we need it? So the idea here is that at the beginning of the training, the uncertainty that we allow for, the degree of optimism can be high enough to select sometimes not that good actions. But when we have a lot of data points, we become much more certain of the relative distribution of the relative position of the distributions of rewards in each case. So thus we can increase the certainty of the confidence interval here. And when we increase the certainty of this confidence interval, we decrease the p, because p is basically 1 minus the probability that the sample is bounded in this confidence interval, in this notation. So hence we decrease p during training to shrink the confidence interval even further and kind of guarantee the optimal solution at the end of the training. Because when we shrink the confidence interval in the limit, we would select the optimal action in the limit always. Whereas if we have the confidence interval which allows for greater deviation, we would continue exploring with some extent, even though after some time we would not need that much of exploration. So we can use some kind of schedule for parameter of probability, and this would give us this formula for computing upper confidence bounds. So now we come to the complete algorithm called UCB1, where we select action with the highest upper confidence bound of distribution of Q values. So this gives us argmax over all actions, Q function for this action, which is here sample mean plus squared root, which we derived from Hobding's inequality using the decaying P schedule. So, and this algorithm is guaranteed to achieve logarithmic total regret in all environments, which is a good achievement, because here there are no hyperparameters, and we basically rely on power of probability theory and statistics and compare the upper confidence bounds for distributions to select the one which is likely to be more promising than the rest. So, any questions so far on confidence bounds?
Actually, I don't get this formula. So does it, well, the final one, does it mean that our action changes based on something that is under square root? Seems kind of counterintuitive.
So yeah, so here everything that goes after the argmax is actually in the
you
brackets.
forgot the brackets. Okay.
Yeah,
okay.
yeah.
Mm-hmm.
So it's argmax of the sum of Q value of action plus the squared root of 2 log t divided by number of actions. So t
okay,
here.
So yeah, we pretty much take the upper confidence interval for the Q value, which is QA plus the square root. Okay.
Yeah, yeah. So t here is the number of total steps. So the number of all steps for all actions combined, and nt of a is the number of times that we have selected this action. Yeah. So UCB1 achieves logarithmic total regret, which is fine. And let's discuss a slight extension of upper confidence bounds, which is called Bayesian upper confidence bounds. So as you had the statistics course, you probably know about the Bayesian approach in the statistics. And this approach can also be applied here in exploration in reinforcement learning. So before, when we derived UCB1, we only looked at the empirical distributions. We gathered some statistics, we gathered samples of each action, and looking only at those samples, we estimated upper confidence bounds for true expectations of these distributions. So apart from that, we can assign some prior information to this process. So for example, if you are working at some environment that you have as the human, as the engineer, that you have some knowledge about. So for example, if you are training some autonomous vehicles, you probably know and you probably have the belief that it's typically not very, how should I say it? Not very optimal to use very intensive acceleration when you're driving a car on the roads. So although at some situations it is required or it is necessary to use very intensive acceleration, for example, when you try to avoid some accident, sometimes you need to accelerate. But generally speaking, it is not very safe. It is not very pleasant for the passengers. It is not very good for the car. In bad road conditions, it can lead to loss in ability to operate the vehicle. So priorly, the fast and intensive acceleration is not very optimal. So as we already know something about the problem, we can assign some prior distributions to the actions for our algorithm to train. So for example, if you're training the operating control of the autonomous vehicle, for example, you can do something like assign prior distributions to different actions where the prior information, the prior Q value for very intensive acceleration would be less than for less intensive acceleration. And by using this prior information, you can add bias to the statistics that you have gathered. And in this example, you would compare not the empirical probability distributions, but you would compare the posterior probability distributions with respect to the prior distributions and with respect to the data that you have collected. So of course, you can not only inject some bias, you can assume that the distributions come from some families which you have good idea that represent the data well. So for example, you can assume that the distributions are always centered for each Q value, which is logical, or you could assume that the distributions have a long tail or something else. So basically you could introduce the external information about the problem that you know about. So using this external information, we can compare the same statistics of upper confidence bounds, but instead of using raw empirical distributions, we can compare the posterior distributions. This can be more data efficient on the one hand, and on the other hand, well, it's obvious that they incorporate some external information. So this gives us the Bayesian upper confidence bound sampling, which is the same as simple upper confidence bound sampling, apart from the way that we compute the upper confidence bound. So here we simply compute the corresponding percentile of the posterior distribution, and this is our upper confidence bound. So that's upper confidence bounds. One other way to use to do exploration is called probability matching. So it is slightly different, but generally they represent the same idea. So upper confidence bounds, informally speaking, can be thought of being too optimistic. So if we, for example, look only at the 95% percentiles, this may seem too naive to some extent. So why would we compare percentiles close to 100%, you may ask? So these percentiles can be not very real life. So these percentiles actually represent the value of the sample kind of very distant from what we get on average, formally speaking. So why don't we compare expectations, you may ask? So one way to formalize it in a different way, to formalize the exploration in a different way, is to select action according to the probability that this action is the optimal. So this gives us some different properties than simply comparing upper confidence bounds. So how to formalize it? Well, we have three distributions, and we want to compare samples drawn from these distributions, and we want to estimate probabilities that one distribution is better than the others. And we want to estimate these probabilities in explicit way. So we would get something like this. Probability of action A given our history, HT, is the probability that the action corresponding, that the Q-value corresponding to this action is greater than the Q-value corresponding to other actions. So we want these explicit probabilities, and we would sample actions according to those probabilities of optimality. So how can we do this? One way to do it is called Thompson sampling, which involves some Bayesian approach. So we can compute posterior distribution for each action, and we can sample from each distribution a number of points, and we can deduce probabilities from these samples. Or we could sample only one action from each distribution, only one Q value, sorry, from each distribution, and select the action with the highest Q value. So in the limit, this will give us sampling with proportions exactly equal to the probability that the Q value is greater than the Q values for the rest of the actions. So this is a slight modification, which in practice works very well in some environments. So in some environments, it is much better to do this kind of sampling than the upper confidence bounds, because, well, informally, it is clear that sometimes upper confidence bounds can be too optimistic. And even though some upper confidence bound can be large enough, the expectation, well, to understand that upper confidence bound is not large enough, we would lose some time doing sampling for this suboptimal action. And using this probability matching strategy, we can understand that this action is not better than the others, using less trials, so to say. So that's another way to do it. There was a question in the chat. Why is the distribution always Gaussian? Well, in this example, it's simply because it is intuitively more easy to compare different distributions from the same family. So if there were distributions with different curvature, with different skew, this would not be as easy to illustrate this on a small example. Also, generally, if you compute some posterior statistics, normal distributions are the most common choice because they have good properties. That if you have a prior normal distribution, you would get the posterior also normal distribution. And the estimates in the Bayesian approach, in case of normal distribution, the estimate becomes much easier. So the formulas become much more pleasant to work with. So generally speaking, if you do some kind of prior posterior statistics, normal distributions are probably the most common if we know nothing about the problem or some specifics. So it's just the most common way to compute these posterior statistics. So let's kind of summarize what we have covered today. So generally, there is an exploration versus exploitation trade-off in reinforcement learning. In particular, this means that we always have some imperfect information about the world, and we have a dilemma whether to do exploitation by following our current understanding, or whether to learn something more about the parts of the world that we are not so sure about. And in practice, there are different strategies for using data for making this decision, ranging from very simple algorithms called greedy, Epsilon greedy softmax sampling that we have seen before. And there are more probabilistically sound approaches to using previous statistics and advanced properties of the distributions to understand which actions require exploration more than the rest of them. So we can, first of all, we can use the concept of upper confidence bound and compare how good the actions can probably be if we are optimists and believe that the true distribution mean can probably lie somewhere around the upper confidence bound. So apart from that, we can compute the exact probabilities that one action is greater than the other based on our previous observations. And there is an algorithm called Thompson sampling, which computes these probabilities by drawing samples from the posterior distributions of Q values for or rewards for each actions. So we can compare and measure this algorithm using the regret concept, but generally speaking, the end metric for all of the exploitation schemes is the end reward that your agent achieves. So typically, if you are not playing slot machines, in most cases, you work in some kind of simulator. And in this case, the final metric would be the reward that you get once you deploy your model to the real application. So a good exploration algorithm is essentially the one which allows for better training in terms of training efficiency to converge faster or training effectiveness to get the highest reward in the trained state. So that's it. If you have any questions, we have some time to discuss them. And we have quite few time to discuss the practice notebook, which will be the homework assignment. But I believe it is pretty clear from the notebook itself. So just to scan through the notebook, what's the homework about? So this week we have an assignment which is dedicated to exploration strategies, and basically just to implement some easy versions of the algorithms which we have discussed and compare them in the simulated environment. So we have the Bernoulli Bandit, very simple problem with only one state and k actions. So this is the Bandit from the example with the slot machines. And we would implement several strategies: Epsilon greedy, upper confidence bound, and Thompson sampling. So at the end, you would get something like this in this example. So the plot is given to you, so it would be easier to understand whether you have bug in implementation or everything works correctly. So that's the first part. There is also a second part, which is different from the first one in terms of non-stationarity. So stationarity is basically the fact whether the parameters of the environment change over time or not. So in the first part, the environment is stationary. It means that all the probabilities of success of each action is fixed and does not change over time. So it's easier to understand which one is the optimal than it is in the case of changing probabilities of success. So that's the non-stationary part. And basically, the probabilities would change depending on the time. And they would fluctuate in a very crazy way. So at each point in the time, the optimal action would be completely different. And the task here would be to modify the agent slightly or modify in a complete way to account for this change in the environment dynamics. So here you would implement your agent, which would perform ideally better than the others in this changing environment. So that's the task in this assignment. So you could also do the bonus part with the implementation of Gittin's index and get 3 bonus points, but that's not obligatory. This means that the 100% score for this homework would be 4 plus 3, 7 points. And you would get 3 points as the bonus if you want to account for other homeworks, or if you just want to implement something else and learn about the Gittin's index. So that's it. I believe that's all from my part. If you have any questions, we can discuss them now, or you can write in the course chat in the Telegram.
Do we have formulas there in this notebook? Are they typed in, or should we type them in?
Well, basically, you have the general pseudocode for UCB agent and for Thompson sampling, from which you can understand kind of what to put in the code. I believe it's very easy, and you would need to invent your own strategy for this non-stationary case. And here you can do whatever you want. Basically, you can modify Thompson sampling, you can modify UCB. Just do whatever you want to perform better in this non-stationary case.
I see.
All right, so if no more questions, then have a nice week. See you next Tuesday.
Thank you. Goodbye.